Hello everyone, and welcome back to some more remote learning. In today's video, we're finally going to go over the chain rule. So we've discussed 6 differentiation rules thus far: the constant rule, the power rule, the constant multiple rule, and the sum rule, which we did in one example worksheet. And then we moved on to the product rule and the quotient rule. And now we're going to learn another technique for evaluating the derivative, the chain rule. So let's take a look below. So the chain rule is for when we're trying to take the derivative of a function of a function, so the composite of functions. So if I'm trying to find the derivative with respect to x of f of g of x, well, how exactly do I do that? We start by taking the derivative of the outermost function, so we're going to do f prime of g of x, and then we're going to multiply that by the derivative of that inner function, so times g prime of x. So f prime of g of x, the derivative of our outermost function, so leaving that inner function the same, and then we'll multiply by the derivative of that inner function. So the helpful hint for the chain rule is to figure out what is your innermost function, what's your outermost function, and you can apply the chain rule multiple times. Maybe we'll have a function within 2 other functions, but you have to really pick apart the different functions that we have composites of. So let's take a look at this first example. In this first example, we have x cubed plus 4, that entire quantity squared. So we're going to set this inner parentheses, this x cubed plus 4, that is our g of x. So if that's our g of x, that function is squared. So our f of x is really x squared. So when we take f of g of x, if g of x is x cubed plus 4, remember we take that entire function and we're plugging it in for x. So taking x cubed plus 4 and plugging it in for x, that's how we're going to get our x cubed plus 4 squared. So my outermost function is squaring, and then my inner function is that x cubed plus 4. So again, if g of x is that x cubed plus 4, we know then that f of x is x squared. So we're going to take the derivative of f of g of x and multiply that by the derivative of g of x. So let's first start by taking the derivative of f of x. Well, the derivative of f of x is going to be taking the derivative of x squared gives us 2x. But I don't want the derivative of f of x, I want the derivative of f of g of x. So instead of having 2x, I'm going to have 2 times what g of x is, x cubed plus 4. So that's my f prime of g of x, 2 times x cubed plus 4, and then I need to multiply that by the derivative of g of x. So g prime of x, that derivative, the derivative of x cubed plus 4, is 3x squared. So overall, my derivative is 2 times x cubed plus 4 times 3x squared. So I have 2 times x cubed plus 4 times 3x squared. This simplifies down to 6x squared times x cubed plus 4. And let's double check by actually distributing this binomial out. So x cubed plus 4 squared gives us, well, x cubed times x cubed is x to the 6th, plus 4x cubed plus 4x cubed is 8x cubed, plus 4 times 4 is 16. Taking the derivative of this, we'll get 6x to the 5th plus 24x squared. Is that equivalent to this? Yeah, it is. If I distributed this 6x squared through, I'd get 6x to the 5th plus 24x squared. So you can see that it is indeed equivalent. So again, when taking the chain rule, we start with our outermost function, find the outermost function's derivative of g of x, and then multiply it by the derivative of that inner function g of x. So let's take a look at our next example, 6x cubed plus 2x minus 4 all raised to the fourth. Well, our innermost function is this 6x cubed plus 2x minus 3, and our outermost function is raising that to the fourth. So if I have something raised to the fourth, what's the derivative? Well, it's going to be using the power rule. I bring that 4 down in front, and then I decrease that exponent by 1. So starting with my outermost derivative, I know that I have 4 times whatever that function is, then cubed. So my innermost function is that 6x cubed plus 2x minus 3. So I have 4 times 6x cubed plus 2x minus 3 cubed. If you want to think about this as my x, what's the derivative of x to the fourth? That's 4x cubed, but my x is really that innermost function of 6x cubed plus 2x minus 3. But that's not the complete derivative, because then I need to multiply by the derivative of that inside function, which the derivative of my inside function is the derivative of 6x cubed plus 2x minus 3, which is going to leave me with multiplying by an 18x squared plus 2, because the derivative of 6x cubed is 18x squared, the derivative of 2x is 2, the derivative of 3 is just 0. So you can see here is my f prime of g of x, and there's my g prime of x. So one more time, we take the derivative of the outermost function and work our way inside, keeping those inner functions the same until we go to take their derivatives. Now, before we really dive into this worksheet, let's revisit the function e to the x. Remember, e to the x is the only function where the derivative of e to the x is itself, e to the x. So how exactly does the chain rule apply to e to the x when our x is really some function of x? Well, remember, our outermost function, we take the derivative of that, and then we take the derivative of our innermost function. So if our outermost function is our e raised to some power, the derivative with respect to x of e to the f of x is going to be e to the f of x times f prime of x. You can see here's the derivative of my outermost function. The derivative of e raised to some function is e to that function, but we have to remember to multiply by the derivative of that function it was raised to, so f prime of x. So the derivative of e to the f of x is itself times the derivative of f of x. So now that we've gone over the chain rule quickly again, let's do example 1. In example 1, we're going to find the equation of the tangent line 2f of x equals 4x minus 6 to the fifth at x equals 2. Now remember, in order to find the equation of the tangent line, I need the slope of the tangent line and I need the function at that point. The slope of the tangent line is the derivative, so I need to find the derivative at my point when x is equal to 2, and I also need to find the point on my function when x is equal to 2. Let's start by finding that point on the function. So f of 2, knowing that my x value is 2, is going to be 4 times 2 minus 6 all raised to the fifth. 4 times 2 is 8, 8 minus 6 is 2, so 2 to the fifth is going to give me 32. So my point is 2, 32. So if that's my point, now I need to just find my slope. So the derivative of my function at x equals 2 is the slope of my tangent line. So f prime of x is going to equal, taking the derivative, what rule are we going to have to use? We're going to have to use the chain rule because we have some function raised to a power of 5. So our outermost function essentially is some x to the fifth. How do we take the derivative of x to the fifth? That becomes 5x to the fourth. But we don't have an x in here. We have a 4x minus 6. So as opposed to 5x to the fourth, this is 5 times 4x minus 6 to the fourth. And then I need to multiply finally by the derivative of that inner function, the derivative of 4x minus 6, which is going to be a 4. So simplifying this down by combining the 5 and 4, I'll get 20 times 4x minus 6 to the fourth. So if that's my derivative of x, I need to find the derivative at x equals 2. So f prime of 2 is going to equal 20 times 4 times 2 minus 6, all raised to the fourth. 4 times 2 is 8. 8 minus 6 is 2. So I'm going to have 20 times 2 to the fourth. 2 to the fourth is 16. 16 times 20 is going to be 320. So I have 320. So 320 is the slope of my tangent line at x equals 2. So because I have a slope and a point, I'll go ahead and write this in point slope form. So we'll have y minus y1, so y minus 32 equals m, which our slope m is 320, times x minus x1, x minus 2. And there we have it. That's the equation of my tangent line to my function at x equals 2. And again, I found that derivative by using the chain rule. So let's get a little more practice with working with that. So in example 2, we're going to evaluate each of the following. Now remember, taking the derivative of e to some function of x is e to that function times the derivative of that function. So taking the derivative of e to the 2x, that's going to be e to the function, e to the 2x, times the derivative of that function, times the derivative of 2x. So that's going to give me e to the 2x times 2. Or a more common way of writing this is 2e to the 2x. That's my derivative in part A. Let's look at part B. For part B, if you notice, this is a similar derivative that we did an example worksheet or two ago, 3/2 cosine squared of x. I believe it was part H on our trig derivative example worksheet. And this is part H when it was simplified down. Now remember, we didn't know how to do the chain rule then, so we had to find the derivative of this using the product rule, doing 3/2 cosine of x times cosine of x. However, now that we do know the chain rule, we can combine that with the constant multiple rule by pulling that 3/2 out in front and just find the derivative of cosine squared of x. So if I pull that 3/2 out in front, I'm going to then multiply it by the derivative of cosine squared of x. Now it might be easier to think of cosine squared of x as cosine of x, that entire function squared. So this I'm going to rewrite as the cosine of x, that entire function squared. So now it might be a little bit easier to see what that outermost function is. It's some quantity squared. So if we're taking the derivative of x squared, that would be 2x to the first. But I'm not taking the derivative of x squared, I'm taking the derivative of cosine of x squared. So leaving my 3/2 out in front, that outermost derivative is going to be multiplying by 2, and then I still have this cosine of x. However, it's now raised to the first power. You can see I just dropped that exponent down in front and then decrease that exponent by 1 to get 2 times cosine of x to the first, which is 2 times cosine of x. But my work's not done, because after that, I need to multiply by the derivative of my inside. What's the derivative of cosine of x? That's a negative sine of x. So let's go ahead and simplify this down. You can see that my 2 will cancel out with the 2 in the denominator to leave me with a negative 3, pulling that negative out in front, negative 3 cosine of x sine of x. And this should be the same exact result that you got when you did the product rule, except doing the chain rule was a lot easier. We just used the power rule, then made sure to multiply by the derivative of that inside, and then simplified it down. Let's move on to part C. In part C, we're going to be taking the derivative with respect to t. So we have the sine of t squared plus 4t minus 1. Again, the most important part about this chain rule is figuring out what our outermost functions are and what our innermost functions are. So figuring out the ordering of those functions. My outermost function, you can see, is the sine. So I have the sine of my innermost function. So because the sine is my outermost function, and then I have this t squared plus 4t as my innermost function, I have to take the derivative of the sine of that function first, and then multiply by the derivative of that function. So the derivative of the sine of x, we know, is a positive cosine of x, but I don't have x. I have the sine of f of x. So the derivative of that is the cosine of f of x times f prime of x, or in this case, cosine of f of t times f prime of t. So this becomes cosine of t squared plus 4t minus 1. There's me taking the derivative of my outermost function, and then I'm going to multiply this all by the derivative of my innermost function, which is going to be 2t plus 4. So the derivative, 2t plus 4 times the cosine of t squared plus 4t minus 1. Let's move on to the next part of this example. We're going to be taking the derivative with respect to u of the cube root of u to the 5th minus 9u. Again, what's the ordering of our functions? Well, we can see that that inner function is u to the 5th minus 9u, and that entire function is, well, we're taking the cube root of it. I like to rewrite this as the derivative with respect to u of my innermost function, which is u to the 5th, minus 9u, but it's that quantity raised to the 1/3, because taking the cube root is the same as raising something to the 1/3. It's just easier to write it like this so that I can visually see the power rule take place. So taking the derivative of my outermost function, it's raising it to the 1/3, so I drop my exponent down in front. So I'm going to bring this 1/3 down in front, and then I'm going to decrease it by 1. So I'm going to have 1/3 times u to the 5th minus 9u, all raised to the 1/3 minus 1, or 1/3 minus 3/3, is going to be negative 2/3. And then remember, I have to multiply by what? The derivative of that inside function. So the derivative of u to the 5th minus 9u is going to be 5u to the 4th minus 9. And again, make sure you're putting that in the parentheses, because we have f prime of g of x times g prime of x, that entire derivative of our inner function. So if I wanted to simplify this down and rewrite it, if you guys know me by now, I'm not crazy about negative exponents in my answer, so I like to write them as positive exponents in denominators. So my numerator is going to be 5u to the 4th minus 9 over my denominator of 3 times u to the 5th minus 9u to the positive 2/3. And there we have it. That's my derivative in part D. Now, for these 4 quick examples, we were mostly dealing with a single composite, so f of g of x. But what if we have f of g of h of x? What if we have f of g of h of q of x or p of x? What if we have multiple functions within other functions? Well, we're going to get into some examples of those next. So now, getting into a little bit more complicated derivatives, using the chain rule multiple different times in a problem. For each of the following example 3, we're going to be evaluating the derivative. But remember, one of the most important things is figuring out what your outermost function is, and then working your way to the innermost function, continually taking the derivative of each of those respective functions. So before we really dive into example A, let's see how many functions we're dealing with. Well, our outermost function is e raised to something. So So we have e to the sine of x cubed. The next function is going to be the sine of something, so the sine of some function, and we have that function within that sine function that's going to be that x cubed. So you can see that our outermost function is e raised to some function, and then our next function is the sine of some function, and then that innermost function is our x cubed. So we're going to take the derivative, applying this chain rule. So f prime of x is going to start by, well, taking the derivative of e to some function is e to the sine of that x cubed. The same exact thing. Whatever we had e raised to, it's e to that, and then we multiply by the derivative of that. So now we're going to look at the sine of x cubed. Well, we've done a chain rule similar to this up above. We need to first start with that sine function. What's the derivative of the sine of something? It's going to be cosine of that function. The derivative of sine of x is cosine of x. So we're going to have cosine of that function. So this all gets multiplied by the cosine of x cubed. But then finally, we're taking the derivative of that innermost function, the derivative of x cubed. So that gets multiplied by 3x squared. So writing this all out, we have 3x squared e to the sine of x cubed, all multiplied by the cosine of x cubed. And that's the derivative in part A. Again, we started with that outermost function, took that derivative, then did the next function's derivative, and then finally multiplied by that innermost function's derivative. Moving on to part B, we have 3x to the fifth minus 4x times the tangent of 2x to the sixth. A function times another function, we're going to have to do a little bit of product rule here. So let's do the bookkeeping like I showed you in that product and quotient rules example worksheet. So my f of x is going to be that first function of 3x to the fifth minus 4x, and my g of x is going to be that second function of the tangent of 2x to the sixth. F prime of x, taking the derivative of f of x, 3x to the fifth minus 4 becomes 15x to the fourth minus 4, and then g prime of x, how do I take the derivative of the tangent of 2x to the sixth? This is where that chain rule comes into play. My outermost function is the tangent, and my innermost function is that 2x to the sixth. So the derivative of the tangent of x is secant of x squared. But I don't have that x, I have that function. So the secant of my function, that quantity squared. So I'm going to have secant squared of 2x to the sixth, and then what do I multiply by? The derivative of that inside, the derivative of 2x to the sixth, which is 12x to the fifth. Now, just finish out this product rule. First times the derivative of the second, plus second times the derivative of the first. So my dy dx, the derivative of y with respect to x, is 3x to the fifth minus 4x times 12x to the fifth times the secant of that 2x to the sixth, that entire quantity squared, and then I'm going to add that to second times the derivative of the first, which is going to be that 15x to the fourth minus 4 times the tangent of 2x to the sixth. And there we have it. You can see that I have my first times the derivative of the second plus second times the derivative of that first, all in here. And remember, multiplication is commutative, so the order doesn't matter. Just make sure I take one function and multiply by the derivative of the other, and then add that together to the other function multiplied by the derivative of the other. So in this case, in example B, we use the chain rule within the product rule. In example C, looks like we're going to be doing some chain rule within the quotient rule. And what's the quotient rule again? Low d high minus high d low, all over low squared. F prime of x, writing this out, not taking any derivatives yet, I'm just going to write that I'm going to be taking the derivative. I'll have my lower function, my denominator, x cubed plus 4 squared times d high, the derivative of e to the 3x, minus high, my numerator function, times the derivative of my denominator, d low, the derivative of x cubed plus 4, that quantity squared, and that's all over low squared x cubed plus 4 squared squared, because x cubed plus 4 squared is my denominator and low squared is that squared. So now let's write this out. I've got f prime of x as x cubed plus 4 squared times the derivative of e to the 3x is e to the 3x times the derivative of 3x. So that's going to be 3e to the 3x, very similar to an example we did above. I believe we had e to the 2x, and we got 2e to the 2x. So e to the 3x becomes 3e to the 3x. And then we're subtracting e to the 3x times, here we go, here's another chain rule. What's our innermost function? Our innermost function is that x cubed plus 4, and we're squaring that entire quantity. So we start by bringing down this exponent and then decreasing it by 1, and then we'll multiply by the derivative of that inside. So we're going to have 2 times x cubed plus 4 to the first, which is just that x cubed plus 4, and we multiply by the derivative of the inside, which is going to be a 3x squared. And then finally, that's all over my denominator squared, so x cubed plus 4 squared squared. 2 times 2 gives me 4. So that's all over x cubed plus 4 to the 4th. Now, on your own, simplify this down. In your numerator, you can see that you're going to have some greatest common factor of a 3e times x cubed plus 4, because you have that in each of your terms in your numerator. You have your 3e to the 3x times x cubed plus 4. You'll be able to pull out of each of them, simplifying that down a bit. But I'll let you do that on your own. For now, let's move on to part D. In part D, we're going to have to do what? The product rule. So we can either do bookkeeping or we can just talk about it. Since I did some bookkeeping above showing you how it worked, let's just talk through the product rule. So when I find h prime of z, I'm going to do first, which is the square root of z, times the derivative of my second, the derivative with respect to z of z to the 4th minus 8, plus second, which is z to the 4th minus 8, times the derivative of my first times the derivative with respect to z of the square root of z. And actually in this case, I don't think there's any chain rule even involved. So we're going to take the square root of z and multiply it by the derivative of z to the 4th minus 8, which is going to be 4z cubed, and then we'll add that to z to the 4th minus 8 times the derivative of z to the 1/2, because the square root of z is z to the 1/2, so that'll be times 1/2 z to the negative 1/2, or 1 over 2 times the square root of z if you don't want that negative exponent. But let's go ahead for practice. Let's switch this problem up just a bit and actually make it something where the chain rule is required. Let's say that we had z to the 4th minus 8, and we had that all raised to a power of 3. Now for part E, we have the cosine of x to the 5th. What's our outermost function? And then we'll work our way inside. So our outermost function, you can see, is going to be that cosine of x to the 5th. And then our next function is going to be the cosine of just that x to the 5th. And then finally, we'll finish out with x to the 5th. So starting with that outermost function's derivative, what's the derivative of cosine? That's going to be a negative sign. So we're going to have that dy dx, first of all, equals negative sine of, I'll leave everything else as is, cosine of x to the fifth. And now I'm going to multiply by the derivative of that next function, which is the cosine function of that x to the fifth. So the derivative of cosine again is a negative sign. So this gets multiplied by negative sine of, and then I'll leave my inner function still as is, x to the fifth. And then finally, I'll multiply by the derivative of that innermost function. The derivative of x to the fifth is 5x to the fourth. A negative times a negative is going to give me a positive, so this derivative is going to be 5x to the fourth times the sine of the cosine of x to the fifth times the sine of x to the fifth. And there we have it. That's the derivative of the cosine of x to the fifth. Starting with that outermost function and working our way in. Not doing anything to those inside functions until we take its derivative. In part F, looks like we're going to be using what rule? The quotient rule, because we have some numerator over some denominator, two separate functions. I'm not able really to cancel out that denominator function, so we're going to do the quotient rule. So dy dx is going to be low, which is e to the 4x cubed plus 2, d high, so I'm going to write that as the derivative of 2x plus 3 to the 5 halves. I think since we're still getting used to this chain rule, I'll take the derivatives in the next step. Let's just write out the process. Minus high, which is going to be 2x plus 3 to the 5 halves, and that gets multiplied by d low, so the derivative with respect to x, since that's our variable in this problem, e to the 4x cubed plus 2, and this is all over low squared. So e to the 4x cubed plus 2, that entire quantity squared. Now, finishing this out by actually computing those derivatives of denominators and numerators, we'll get e to the 4x cubed plus 2, and then multiplying by the derivative of our numerator, chain rule. We have some inner function, and that is all raised to the 5 halves. So I start by bringing down my exponent using the power rule. I keep my inner function the same for now, and then that gets raised to the 5 halves minus 1, so 5 halves minus 2 halves is 3 halves. But I need to remember to multiply by the derivative of that inside. So that's 2x plus 3. The derivative of that is 2. Now in this case, I'll simplify as I go because 2 will cancel out with 2 to leave me with 5 times 2x plus 3 to the 3 halves. So I'll go ahead and erase this now, just so I have a little bit more room for work. Now I'm going to subtract 2x plus 3 to the 5 halves, and that gets multiplied by the derivative of my denominator. Remember, e to the f of x, the derivative of that is e to the f of x times f prime of x. So I'm just going to rewrite it, e to the 4x cubed plus 2, but then I need to multiply by the derivative of that f of x, the derivative of that inner function, the derivative of 4x cubed plus 2, which is 12x squared. So there we have it. That's my numerator, and you can try to simplify this down by pulling out those greatest common factors. For example, in each, we have e to the 4x cubed plus 2, and we also have at least a 2x plus 3 to the 3 halves in each of these problems. Obviously, we have an extra bit with that 5 halves, but if you pull out the greatest common factor, the problem will be simplified down further. But finishing out that denominator, we multiply the exponents together when we have one exponent raised to another power. So this is going to be e to the 2 times 4x cubed plus 2. And if we wanted to distribute that through, that would be e to the 8x cubed plus 4. That's our derivative in part F. So there we have it, using the quotient rule, low d high minus high d low all over low squared. And within that quotient rule, we actually had a couple different chain rules. Now for part G, our function is f of t equals the cosecant of t e to the t. So the function is in terms of t, so we're going to be taking the derivative with respect to t. First, let's look at our different functions. Our outermost function is that cosecant function, so we have the cosecant of something, so we'll start by taking the derivative of cosecant, but then our innermost function, look at it, it's actually the multiplication of two separate functions. So we're going to do a product rule within this chain rule. So let's get started. F prime of t, starting with that outermost function's derivative, the derivative of cosecant is negative cosecant cotangent. So it's negative cosecant of the function times cotangent of the function, and then finally times the derivative of that function. So we'll have negative cosecant of t e to the t times cotangent of t e to the t, but we still need to multiply this by the derivative of t e to the t. Now I wrote it like this to help us keep track, because the derivative of t e to the t, we're going to need to do the product rule for. So let's continue on. We'll have negative cosecant t e to the t, cotangent of t e to the t, and now we multiply all of that by the product rule, the derivative of t e to the t. So if our first function is t and our second function is e to the t, first times the derivative of the second plus second times the derivative of the first, and you could also use that bookkeeping trick. However, I'm going to write first function, which is t, and I'm going to write out the derivative of the second. So we need to take the derivative of the second still, and then I'm going to have my second function, e to the t, and I'm going to multiply that by the derivative of my first function, t. So I'm just writing out each of my steps here. I still need to take those derivatives. I just didn't want to do it in my head so that I could keep track. So our final result is going to be negative cosecant of t e to the t times cotangent of t e to the t, and that all gets multiplied by t times the derivative of e to the t is e to the t plus e to the t times the derivative of t, which the derivative of t is just 1. So this just stays as t e to the t plus e to the t. And that's our derivative for part G. And remember that this is multiplied by, don't drop those parentheses, that's the derivative of our innermost function. It was using that product rule. If you drop the parentheses, then this derivative will be incorrect. We need to make sure that we have that negative cosecant and cotangent of that function multiplied by the derivative of that innermost function, multiplied by both parts. And lastly on this worksheet, we have g of x. We're going to find the derivative of x cubed plus 2 over 2x to the 5th minus 6x plus 2 all raised to the 4th. So this is actually going to be a quotient rule within a chain rule, because our outermost function is something raised to the 4th, but our innermost function is going to require a quotient rule to take the derivative. So let's start with that outermost function's derivative. When we go to write g prime of x, it's going to be, well, for the power rule, we drop the 4 or our exponent down in front and then decrease it by 1. But remember, that inner function is going to stay the same until we go to take its derivative. So this is going to be 4 times x cubed plus 2 over 2x to the 5th minus 6x plus 2, all raised to the 4 minus 1, all raised to the 3rd. And then we're going to multiply that by the derivative of that innermost function, which is going to be the quotient rule. So we're going to multiply that all by low d high minus high d low all over low squared. So let's write this out. Low is going to be 2x to the 5th minus 6x plus 2 times the derivative of our high, the derivative of x cubed plus 2 is 3x squared. So there's my low d high. Now I'm going to subtract high d low. So high is x cubed plus 2 And the derivative of low, the derivative of 2x to the fifth minus 6x plus 2 is 10x to the fourth minus 6. So there we have it. That's my low, d high, minus high, d low, and that's all over low squared. So that's going to be all over 2x to the fifth minus 6x plus 2, all raised to the 2. 2x to the fifth minus 6x plus 2, all squared. And that's my derivative for the last part. Now, let's talk about how we could potentially simplify this. And let's think about it. We don't necessarily have to write it out, but we'll think about it. Because this exponent is applied to this entire fraction, I can distribute it in. So I can distribute the 3 into my numerator and into my denominator. And when I do that, then I'm able to combine my denominators because I have 2x to the fifth minus 6x plus 2 cubed times 2x to the fifth minus 6x plus 2 squared. So I'd be able to combine those denominators by adding the exponents because it's the same base. So that might help me out a little bit, but then in order to combine my numerator, I would have to distribute this out because of this subtraction in there. So I could do that and attempt to simplify it down, but for now and for the sake of time, so we can go ahead and end this video, I'll let you do that on your own. So hopefully with this, you got good practice using the chain rule, but not just using the chain rule, also using other differentiation rules throughout this worksheet. And just remember, for the chain rule, we start with that outermost function and work our way into the innermost function, taking derivatives at every step. So if you still have lingering questions, feel free to let me know. And I definitely recommend to continue to practice taking the derivative. Practice all of your rules because they're going to be applied a lot throughout these next couple example videos. But until that next example video, good luck with your online learning.